Okie dokie, let me show you some silly cartoons. We use these just stupid little spheres to represent chemical species, reactants, and products, and how we use those in kinetics types questions to say, well, how fast will the reaction go? How long will it take to proceed from here to here? Which reaction will go faster in the beginning? Yada yada. In any case, first of all, they have to tell you the order of the reaction, or they might ask you to figure out the order of the reaction based on some data. I don't actually know if I have any of those questions here, but I could imagine a twisted, convoluted type question. This, they tell us it's first order, and they say at 0 we start off with 1, 2, 3, 4, 5, 6, 7, 8 reactant units, and I end up after 15 seconds with 1, 2, 3, 4, 5, 6, no wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count that right? 10? I did, 10. 10 green reactants initially at the time equals 0. Then 15 seconds later, as the reaction proceeds in the forward direction, left to right, to make these blue spheres as products, I make 2 blue spheres after 15 seconds, and the rest of the green ones are left unreacted. As soon as they tell me it's first order, I like to think of this equation, if I'm considering how long would it take to do this from here to here. They actually told me the time, but in any case, let me show you what I do. I could come up with letters to stand for whatever the green sphere is or the blue sphere, but let me just use green spheres. Let me imagine that the cartoon is representative of the molar concentration. So if I have 10 units of these green spheres in the beginning, maybe that's 10 molar or a 10th molar or something like that. In any case, I use that number 10, as silly as it sounds, 10 spheres, as a representative number of the initial concentration of those. After 15 seconds, I go to 8 of those, and the time is 15 seconds. I can pretty easily then, can you see, solve for the little k, the rate constant, and therefore if I knew the rate constant, I could find the half-life. And also if I knew the rate constant, I could write rate equals, I didn't do it, I don't think I did it, rate equals little k, which is 0.0149, 1 over seconds, times square brackets of the green spheres to the first power, because they said up here it's first order. Interesting. That's so weird. I have to try that again. Oh, actually, they're continuing with the same question. They say, how long would it take? How many seconds would it take? 15 seconds? No, longer than that. It takes 15 seconds to go from 10 spheres down to 8 spheres. How long would it take to go from 10 green spheres to 2 green spheres and 8 blue products? Well, if you feel like pausing the video right now, you'd be able to try this yourself, but since we already know the constant now from above, let me just use that constant in the same integrated rate law equation. So my constant I found to be 0.0149, 1 over seconds are the units. Good to keep track of the units in many cases. So here's my little k constant right there. I want to go from 10 initially, originally, in the beginning, to 2. From 10 to 2, the natural log of 2, the natural log of 10, hopefully being representative of the molar concentrations, and plug and chug. You use your massive mathematics and algebraic skills to solve for t, 108 seconds. Does that make any sense? I don't know. Let me backpedal for a second. If my half-life is 46 seconds, that's the time it takes for half of the green spheres to go away. So if I start with 10 green spheres, half of them will be gone. I'll have 5 green and 5 blue after 46.5 seconds. So if I want to continue to decrease my green spheres from 10 down to 2, I guess that kind of makes sense that it would take, more time than 40, 50 seconds. A little more than double that, right? Yeah, that's a kind of a mental check on whether our answer is correct or not. Oh yeah, that's a good question here. Which graph would linearize the data? Would give me a linear plot, for example. Would it be the concentration of green spheres versus time? Would it be the natural log of green spheres versus time? What? This choice 3 is the same. I'm silly. What do you know? What about the natural log of the green sphere concentration versus the reciprocal of time? Well, if you've memorized your graphic relationships in first order, second order, zero order, you know it's a natural logarithm of the concentration versus time, and the intercept on the y-axis is that. Again, this is in the y equals mx plus b. Here we have a negative slope, and that's a negative k. Well, yeah, negative k is the slope. In any case, memorize that. Memorize that relationship for the first order. The natural logarithm linearizes everything. Are we continuing with this question? I suppose. If the starting concentration were doubled, so instead of 10 green spheres, I had 20 green spheres, what would happen to the half-life? Oh, interesting. Well, if the concentration doubles, the rate might double, but that doesn't affect the constant, the rate constant. That kind of depends on temperature. So if my rate constant doesn't change, trick question, my half-life doesn't change for the first order. If it is first order, and they continue to say it's the same question, first order. So first order processes keep a constant half-life. If it were second order, interestingly, it would not. The half-life would not stay the same. That's a different topic for a different day, but I think we did integrate the second order reactions and found that the half-life was dependent on the original concentration. So if I double the concentration for a second order, that would change the half-life. But first order half-life stay constant. How about another kind of cartoon question? Here they tell me the rate law, in essence, by saying it's first order with respect to O2, and second order with respect to NO. So we probably told you this is a huge mistake to say, let me just write a rate law based on looking at the reactants. So don't do that. This rate law must have been arrived at through method of initial rates or something like that. Some other study. I don't have the data, but they've told me what it was right here. So perhaps if these cartoons are reflective of the molar concentrations of these gases, it's okay to do this. So here I had 1, 2, 3 O2s and 3 NOs. Put those into the rate law that was described by this first sentence. And I find it's 27K. I don't know what K is. I would need some more data. But I don't have to have it to say relative to this, what does the rate look like here? 1, 2, 3, 4 O2s and 2 NOs come out to 16K. And 1, 2 O2s and 1, 2, 3, 4 NOs. Interesting. So you're right. This is since the NO dependence is second order, I must square that. So that ends up being, in a sense, more important than the concentration of O2. So I think this one would go a lot faster based on second order in NO. 32, 16. It looks like this one might go twice as fast as this one, but not twice as fast as this one, but this one's still faster than this one. Interesting, huh? Here's another silly question. These are good questions. I don't know if it's silly or not. It's silly to think of that we could actually see these little particles, but if we think of in chemistry terms as matter in a particulate nature and the progression of a reaction from reactants to products, then it kind of makes sense. Maybe that's why the motivation behind these questions and comes up on standardized tests a lot. This looks like 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, I believe, reactant particles. They say the rate law for the reaction is, first order, rate equals some constant K times A to the first power. See the 1 there? It's not written, but it's implied, of course. So it's first order in A, so I wrote busted out. Maybe I should have busted out my second order equations, and we'll practice with those later. But in any case, the natural log of my original concentration, natural log of my ending concentration, how much time does it take? So my constant is 0.01. Use my massive algebra skills to solve for time. Comes out to 14 seconds. 14 seconds to go from here to here if my constant is this. Now if my constant were larger, that would mean the reaction would go faster and it wouldn't take as long to get to here. What? That's not even a choice. My goodness. I'm going to have to say D is my best answer. Did I count something incorrectly? I don't know. Let me pause the video and check it out just for a second. Oops, what's up with that? I'll be right back. Thanks, guys. I'm back. I can't see where I made a mistake. Perhaps I thought maybe it was a rounding error, but I don't see natural log of 4. So that's where I end. 1, 2, 3, 4 particles. I have 300 people watching this video or more. You guys can figure out where I made a mistake. Come let me know. But I came out with 13.86, which is close to 12 and a half. But oh, dirt to dirt, that's not right. Fiddlesticks. Well, all right. You guys do the math. This is wrong. Where did I make a mistake? Look at this. The constant they told to me is 0.01. I got it right here, 0.01. So 0.01 here, negative 1.386 divided by 0.01, negative 13.86 divided by 0.01. That gives me right here. No. Yes, okay. 13. No, I can do the math. 1.386 divided by 0.01 equals 139 seconds. So change that, would you? This is a factor of 10 off. That's 138.6 rounded to 139 seconds. So the answer is B, and therefore this is wrong too. Oh man, I feel silly. Anyways, I make mistakes every day. I'm used to it. I'll fix that. I'll try to fix that on the PDF. Now that you're watching the video, you're making fun of me behind my back. Please do so. Here's another interesting rate question. Interesting that the orders can be fractional, 3 halves. Oh my goodness. But anyway, this is very, very similar to one that we saw earlier. And I just count the number of cartoon particles of CO. Looks like CO. CO is like to the first order, and Cl2 is to the 3 halves order. So chlorine is 1, 2, 3, 4. So 4 to the 3 halves power, and 1, 2, 3, 4 to the first power, and it comes out to 32. Change it a bit. Choice B, I have 1, 2, 3 carbon monoxides, and chlorine, Cl2s, I got 1, 2, 3, 4, 5, and that came out to 33.5. It looks like the fastest. Yeah, that's the fastest, isn't it? Everything else. So 3 cartoon molecules here of Cl2, 3 of those, and 5 of those. These 5 here, or these 5 here. And anyways, you just analyze the cartoon and see how many particles you have. Is this making any sense at all? Except for that mistake I made earlier. Gosh, I can move the decimal. Try to fix that on the PDF. Oh, my last example. Yay, you're glad I'm about done talking. Or maybe I had the volume turned down anyway. Not a bad idea. This one they gave a half order in Cl2. Oh my goodness. So another fractional order. We never deal with fractional orders, or we usually go 0 order, first order, second order when we're looking at method of initial rates, and most reactions are first or second order, sometimes 0 order. Fractional order, often with catalysts and some kind of bizarre reactions. But indeed, if this was the rate law, half order with respect to Cl2 and first order with respect to CHCl3. Again, I just look at the cartoons and count 1, 2, 3 Cl2s. So I put 3 here and 1, 2, 3 CHCl3s. Do the math. I omitted the constant in this case to say is proportional to 4 CHCl3s. 1, 2, 3, 4. And it's a little hiding in the hydrogen hiding back there. And 2 Cl2s and 2 CHCl3s and 1, 2, 3, 4 Cl2s. It came out to 4. So if they're wondering which reaction would you expect to have the fastest initial rate, how about the rate that's proportional to this one? Yeah, 5.66. That looks right. Oh yeah, likely the fastest. There we go. Whew. Thanks for watching, guys. See you in class. Practice this some, would you?